Hello everyone, welcome to SDC India 22. My name is Ujjwal Lanjewar and I am presenting this session with Madhavrao Vemuri. Both of us are working at Seagate Technology as storage software architects and currently working on CORTX scale-out object storage. This session is about migrating a distributed storage software stack onto Kubernetes platform. The contents are mainly derived from our experiences of deploying CORTX object storage in a cloud-native environment. The session primarily provides information about various aspects you may need to consider for your storage software stack in order to deploy in Kubernetes environment. The discussion about how to develop applications in Kubernetes, however, is excluded from the scope of this session. Agenda for this session. We will start with a small introduction about Kubernetes and understand why it makes sense to move to Kubernetes and the challenges associated. We're going to use CORTX object storage as a case study to help us understand various concepts we're going to cover here. So we'll take a quick look at the CORTX architecture. We will then talk about deployment aspects of the Kubernetes platform, such as preparing for Kubernetes, deployment architecture, upgrades, extending or scaling out your system which has been deployed in Kubernetes, and so on. We will then touch base on various architecture concepts to be considered for running application in Kubernetes platform. For example, security, observability, availability, durability, performance, and so on. We'll also review the performance benchmark that was carried out recently. And finally, we will conclude with the next steps to be considered once you are ready to move to Kubernetes and various tools, technologies, and frameworks available in the Kubernetes ecosystem. So let's begin with understanding what is Kubernetes. Kubernetes is an automated modular platform that can help deploy and manage distributed software, and it is widely used in a cloud-native environment. Kubernetes provides infrastructure abstraction and mechanisms to make your application highly available and scalable. Community also uses term K8s for Kubernetes. So wherever you see K8s, you should view it as Kubernetes. Why move to Kubernetes? From technical standpoint, it provides a pretty robust platform with several functions that are vital to running any system, such as availability, scalability, security, and so on. From an organization perspective, it is a proven platform and brings simplification in terms of time to market, DevOps, portability, or maintaining a complex system. With Kubernetes, applications can be deployed quickly. This can simplify DevOps process significantly and reduce development and release cycle. With Kubernetes, it's easy to bring changes in terms of platform maintenance, upgrade, without impacting the availability of the system. So considering these aspects, it is strongly recommended to use Kubernetes platform for distributed applications. So how to do this and what are the challenges? Besides skills, certain things that needs to be looked at. For example, the implementation strategy about the changes you will need to bring to your application. This is critical to your decision around adapting Kubernetes in a reasonable time frame and avoiding iterations. Then understanding when you are ready with the sufficient changes in your stack and it is time to move to Kubernetes. Kubernetes has a good ecosystem of tools, technologies, and frameworks to simplify and help with different kinds of application requirements. Sometimes it becomes a challenging task to decide and select the right framework without getting enough insight about them. We will try to address some of these in this session. We are going to use CORTX as an example during this presentation. CORTX was modified to deploy in cloud-native Kubernetes environment recently. What is CORTX? CORTX is an open source S3 compatible scale-out object storage software implementation and provides both data path and management path functions. CORTX also provides a key value store where internal and external metadata can be stored. CORTX is built as a software platform and object storage solutions can be created using CORTX platform by adding additional software or hardware components. CORTX is a highly available distributed object storage and provides various features such as data durability with erasure coding for data and metadata, automatic recovery, observability, replication, compute on storage, extensibility plugins for data access, and so on. CORTX supports many concurrent sessions for accessing object data and can be scaled further when required. For data path, you can visualize CORTX as a two-tier architecture. The base tier serves as a storage layer that implements a set of distributed I/O services and are responsible for storing and retrieving data and metadata. The second tier implements a set of S3 servers to serve data over S3 protocol to S3 clients. For the control path, control services helps with management or access control of data in CORTX. There are certain other services such as messaging or monitor to help with the availability or other similar features. Kubernetes operates on containers which represent an application service. So the very first step towards moving to Kubernetes is to ensure that your application can run in a containerized environment. So what does it mean to running application in container environment? This means first you will need to be able to run your application in user space. In Kubernetes environment, OS swap is disabled. So application should be able to run without the OS swap enabled. You cannot use systemd to start or control your services. This is because Kubernetes does this directly by using application service command line. The next step is to review your application architecture and identify primary and secondary services. Ensure that they are loosely coupled and are able to operate independently. It is recommended to have services that can run in a stateless manner. This makes it easy to ensure quick recovery of the services in case of service failure and migration of services in case of node failure. Then you will need to remove the coupling with the underlying storage systems or network infrastructure by abstracting them. In Kubernetes environment, applications are distributed and deployed as container images. So you will need to change your build and distribution process from distributing or hosting RPMs to container images. In a nutshell, if your software design has followed 12-factor app principles, then it would be relatively easy for you to prepare for the migration onto Kubernetes. About CORTX containerization, CORTX stack has gone through the changes on the similar guidelines. Although CORTX Stack is a user space implementation, there was a dependency on a kernel-based module for transport layer. So CORTX had to switch to user space only transport. Also, CORTX moved to its own memory management mechanism for unmap of pages and resource throttling. S3 server, IO service, control service are the primary services for the deployment, and hence they formed the basis for CORTX images. CORTX also removed startup ordering so that all the services can be configured and started at the same time. CORTX Stack is agnostic to physical storage or network infrastructure. So once you ensure that your application can run in a container environment, you are ready to deploy your application in Kubernetes. Kubernetes infrastructure includes master and worker nodes. Applications are deployed on the worker nodes. Ensure that worker nodes have sufficient resources to accommodate the resource requirement of your application. You need to start with deciding on the deployment architecture in terms of pod structure, the affinity of the pods with reference to the worker nodes, and containers that are going to run various application services. There can be different types of containers depending on the type of job you need to perform. You may also need to define resource constraints for the containers. In Kubernetes, pods can be deployed using various Kubernetes controllers termed as deployments, stateful set, daemon set, and so on. Depending on your application behavior, you may decide to choose one of the options for each pod type. You also need to define interfaces between the pods in the form of Kubernetes services such as ingress, node port, etc. Another important thing is to define the entry point for each container. Kubernetes uses entry point to start your application services. For bootstrapping your deployment, you need to define a set of configuration entries so that Kubernetes can pass those as config map to your application. Then you need to abstract physical storage and network infrastructure. In Kubernetes, you can abstract storage by using persistent volume claims, also termed as PVC, and network by using Kubernetes CNI plugins. You may use init containers to define steps that you may need to run before your application services start. It is recommended to remove startup ordering between the services so that they can be started quickly and in parallel. This will also help in scaling to hundreds of services easily. You may consider implementing readiness probe for Kubernetes to determine that application services have started successfully. Kubernetes ecosystem includes a framework called Helm, which can significantly simplify the deployment process. Let's talk about CORTX deployment. Here's an example that shows 3-node CORTX deployment architecture. A typical CORTX deployment primarily includes multiple data pods, S3 server, and control pods. CORTX container images are built and published on the GitHub platform. The deployment takes an input configuration file that contains information about various pods, storage devices, resource constraints, erasure coding configuration, network ports, and a few other configurations. The deployment job provisions CORTX services and provides them with the required configuration as config map, and then triggers Kubernetes deployment process. Data pod is deployed as stateful set and includes a primary container for IO service, an init container, and a sidecar container. Init container is responsible for the bootstrapping of the service using config map, and it also participates in the upgrade process. The sidecar container helps with the support for failure handling. It communicates with the monitor service to receive events about the failures and then directs the IO service to switch to degraded mode in case of failure. S3 server and control pods have a similar structure and has respective init containers for bootstrapping of the services. Storage devices are abstracted using persistent volume claims. For network, CORTX deployment uses Calico CNI framework. CORTX deployment uses a set of Kubernetes services to facilitate communication between different pods. CORTX can be deployed using a deployment command as per the solution configuration. CORTX uses Helm charts for the deployment of CORTX pods onto Kubernetes. Let's see how a CORTX system is deployed on the Kubernetes cluster. A solution input file is passed to the deployment command. Image section specifies the container images to be used for control server and data pod containers. Then we need to specify the worker nodes where CORTX will be deployed along with the details about storage devices to be used for storing object storage data. There are several other configuration entries to be controlled for controlling various parameters. CORTX deployment command triggers Kubernetes deployment process. This deploys all the CORTX pods in parallel. CORTX deployment process takes about 3 to 4 minutes for a 3-node Kubernetes cluster. So we just saw how easy it was to deploy CORTX object storage software stack onto Kubernetes platform with a simple command. Here is a deployment view of CORTX on a 3-node Kubernetes platform. It shows a single control pod instance active and running. For data pods, we can see there are 6 pods instances, 2 running on each worker node configured with respective storage devices. And then there are 3 S3 server pods with 1 instance running on each worker node. The second window shows Kubernetes node port services for control server and S3 server pods for clients to be able to access them. This is a resource level view of CORTX deployment, which is obtained using Kubernetes metric server. Resource view shows all the application pods and corresponding CPU and memory usage level. This snapshot is showing complete view of an idle system with all the deployed CORTX and Kubernetes system pods along with their statistics. You can see that it is showing a CPU usage level of 10% and memory usage level of 49% at the moment. Kubernetes facilitates various cluster level operations. Kubernetes makes it easy to scale distributed storage applications by adding more pods seamlessly without impacting the availability of the system. Kubernetes provides various upgrade strategies to control the upgrade behavior. It can perform upgrade by upgrading all the container images in a rolling or a blue-green fashion depending on the deployment controller. There are also ways to manage cluster by shutting down specific instances of pods for maintenance of the underlying worker node. CORTX can be extended either for connection or capacity scaling. CORTX cluster includes storage set, which is essentially a set of data pods. For capacity scaling, new data pods can form a new storage set and be added to the existing CORTX cluster. These data pods can be configured either on the existing or new set of worker nodes. For connection scaling, new server pods can be added on the fly. In CORTX, rolling upgrade is performed at the granularity of individual pod types to help with the better availability during upgrade. For maintenance reason, specific CORTX pod instances or the entire CORTX cluster can be shut down gracefully. This is done using Kubernetes scale command set and replica configuration parameter. Observability is one of the important and integral feature of any enterprise storage software. It simply means that application user or administrator should be able to get a view of the system in terms of various activities or events so that they can take suitable action when required. In Kubernetes, this is achieved with the log mechanism. All the information that goes to std out or std error is recorded under Kubernetes logs. Users can then refer to Kubernetes logs to know the details about activities or events in the system. It is also important to generate telemetry and debug information so that they can be collected and provided to support for analysis in case of issues. Debug logs can either be sent to a centralized log server or stored in a special log device configured as PVC. CORTX has options for users to know about the user events through either Kubernetes logging mechanism or through an external Prometheus server, which can collect this information periodically. CORTX presents a view of the system in terms of capacity, deployment, events on the CORTX control path channel. Then CORTX stack generates debug logs which can be stored, collected, and sent to development and support as a support bundle. CORTX also generates various telemetry statistics and events which are sent to a centralized telemetry server for subsequent processing and analysis. Security is another important factor for an enterprise application. There are many aspects of security, such as network security, intrusion, access control, data security, and so on. Security is an integral part of Kubernetes infrastructure. Pods by default are not connected or reachable by any entity in the system. You need to create Kubernetes services to control access between the desired pods or ingress for accessing the system from outside. In Kubernetes, access to the resources are controlled with role-based access control framework. Certain administrative cluster operations can only be performed from Kubernetes master nodes. Kubernetes also provides namespace to isolate one application from the other application deployed in the same Kubernetes environment. There are also security policies that can be applied to the pods. You may also consider container level security, such as enabling SE Linux or restricting shell access to the containers. It is recommended to review all the packages used in your application and perform vulnerability scan for the storage software deployed in Kubernetes environment to ensure security at the application level. In CORTX Kubernetes deployment, all the ports are restricted except for the essential ones and can only be accessed by internal services. CORTX uses load balancer service and node port service together for providing access to S3 server pods from S3 clients and control server from admin clients. For data path, control uses headless service for communication between S3 server and data pods. For data security, control and data paths are access controlled based on user authentication and authorization. Besides this, data stored in S3 bucket can be encrypted. So this was all about the basic deployment related aspects. We also need to consider things like availability, durability, performance, etc. Madhav can provide some insight into some of these aspects of Kubernetes. So I'm handing it over to Madhav.
Thanks, Ujjwal. Let me first talk about availability in Kubernetes and how CORTX is dealing with it. Availability is one of the most desired and integral feature of any distributed storage application. High availability is the ability of the system to be continuously operational for a desired long period of time, even in case of component failures. Kubernetes manages application availability by monitoring and controlling the pods and their containers. In case of containers exceed the memory or CPU consumption beyond a certain limit, Kubernetes restarts them. When a process fails or crashes due to any issue, Kubernetes restarts it. Distributed applications may need to monitor failures in the system to exhibit fault tolerance. Kubernetes API server can provide this functionality. Besides this, liveness probes can also be used to integrate into the Kubernetes system for availability. It is recommended to design a stateless system so that services can be crash consistent and can be migrated to other Kubernetes worker nodes. You can also implement recovery mechanisms to recover data or application state when a failure is resolved. CORTX relies on the load balancer for availability in case of S3 server process failures. It offers seamless IO experience to the user by redirecting traffic to other live S3 servers. For better availability, S3 server retries IO operations in case of transient device or network failures. S3 servers are stateless and can be restarted quickly either on the same or different worker nodes based on resource availability. Control pods are stateless and similar mechanism is followed for them to have the high availability for control path. For CORTX data pods, they have a state and the affinity to the worker nodes for the storage devices used by them. Hence, they cannot be migrated to the other worker nodes in case of storage or node failures. CORTX data path stack maintains a minimal state about its services. There are monitors to observe service or component failures with the help of Kubernetes APIs. In case of node, storage, or network failures, CORTX stack switches to degraded mode with the help of redundancy introduced by network erasure codes. Erasure coding helps in adding parity units to data and metadata, which helps in performing degraded mode operations. Data durability ensures that there is no impact to the data accuracy, even in case of device failure. Users should be able to access correct data during the failure or even after the failure is resolved. In Cortex, durability is achieved by making sure that transactions related to data and metadata are committed to the journal before acknowledgement. Cortex data pods includes these transaction journals, which helps to recover from abrupt failures and offer a crash consistent behavior. Data integrity is maintained by adding checksum for both data and metadata. During get operations, this checksum is validated. Cortex service throttles resource consumption based on the available CPU and memory limits to avoid container restarts. Let's talk about performance now, which is equally important when you are running a system in production. While migrating from host-based distributed applications to Kubernetes container-based infrastructure, it is important to ensure that there is no overhead added to the network or storage performance throughput. We performed a few benchmarks to validate on a multi-node system with default configuration. For network, we used iPerf with TCP over 10 gig Ethernet. We observed that there is a small overhead in terms of performance, and there is a scope of tuning it further. For storage, we used FIO for read and write operations. We observed that write performance was on par. However, for read performance, observed a smaller degradation. This needs to be analyzed to understand the root cause. There are other performance measures such as latency and time to first byte that are also significant from user point of view and needs to be evaluated. Cortex uses Libfabric as a transport layer. So we performed a benchmark of Libfabric using Libfab test with TCP over 50 gig Ethernet on a dual node system configured with Kubernetes CNI Calico framework. We observe that for large number of threads, performance throughput is reasonable with a small overhead. There are certain other Cortex level performance improvements being made in line with the Kubernetes guidelines. Cortex performance work is still in progress, and more details on the same can be found on the Cortex GitHub once it is complete. This completes the overview on availability, durability, and performance aspects. I will hand over to Ujjwal to continue on the other Kubernetes topics.
Thank you, Madhav, for a good overview on the availability, durability, and performance aspects of Kubernetes, and also Cortex availability and durability view. So we reviewed various architecture guidelines to help us understand the changes we need to bring to a distributed storage software stack for migrating onto Kubernetes platform. We also looked at the Cortex architecture and the changes we had to make for Kubernetes platform so far. As a next step, we are in the process of defining Cortex Kubernetes operators, and the details of the same will be published soon. There are many variants of Kubernetes implementations available in the market today. Few of them are listed here. Once you have made required changes in the software stack and are ready to move to Kubernetes, next step is to review and identify the most suitable Kubernetes implementation as per your requirement. Cortex uses open sourced version of Kubernetes. There are various tools available in the market that can help simplify the implementation of Kubernetes deployment infrastructure. Some of them are shown here as an example. Let's talk about them quickly. Helm helps with managing the distributions and deployment. Kubernetes operators help control application at runtime using Kubernetes command set. Prometheus helps in collecting statistics or telemetry information from the system. Istio is another one which helps in implementing service proxy and helps with network traffic management. CNI that we referred to earlier helps with implementation of network framework and policies around it. Knative helps with implementing serverless infrastructure for your application. CSI and COSI helps with the integration of storage software with cloud native environment. These are some of the references for the contents we discussed in the session today. Presentation content will be available after the event, so you should be able to take a look at these. Of these, Cloud Native Computing Foundation, that is CNCF website, provides a good overview on the Kubernetes ecosystem. This concludes the session on migrating distributed software stack onto Kubernetes platform. Thank you for listening to this presentation. If you have any queries related to Kubernetes migration or CORTX, please reach us out and we will be happy to help.